In this presentation, I will talk about multiple regression model. The outline would be first to talk about the multiple regression terminology, provide examples, and interpret the coefficients, then derive the OLS estimates, OLS properties partialing out, talk about goodness of fit, the R squared and adjusted R squared, and then we will continue with the Gauss Markov assumptions, which are the 5 assumptions. I'll also talk about perfect collinearity versus multicollinearity. We'll talk about the unbiasedness of OLS estimators and when we have omitted variable bias, the variance of the OLS estimators, and when we have what happens to variance in misspecified models, and about the Gauss Markov theorem and the blue properties of the OLS estimators. So what is multiple regression model? That's a regression model that has several independent variables, 2 or more. They're also called regressors. The advantages of multiple regression is that it incorporates more independent variables into the model. So unlike the simple regression model that only has one independent variable, this is 2 or more independent variables. So it is more realistic representation of the real world. It explicitly holds other factors fixed. We will talk about this in the lecture, and those factors would be included in the regression as regressors that otherwise will be in the error term if they're not explicitly modeled as regressors. And the multiple regression model also allows for more flexible functional forms, including squared variables, interactions of variables, logs of variables, and so forth. So here's terminology that we will be using. Here, the multiple regression model would be y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus and so on until beta k x k plus u. Here, y is the dependent variable and x1, x2 through xk would be the independent variables. We have k of them. And then u would be the error term and the beta 0, beta 1, beta 2, and so on until beta k are the parameters that we would be estimating. Here I can also talk about x1, x2 through xk, or as an abbreviation, I can denote this as xj, and that would denote any of the independent variables. So I could be referring to x1 or x2 all the way up to xk. And beta j would be any of its parameters, and that beta j would be the parameter of xj. So instead of talking about many of them, x1, x2, and so forth, I will just talk about xj, which means any one of them. And instead of talking about beta 0, beta 1, beta 2, I will talk about just beta j, any of them. The estimated equation would be y hat equals beta 0 hat plus beta 1 hat times x1 plus beta 2 hat times x2 plus all the way to beta hat k times x k. Here, y hat is the predicted value or the fitted value, and beta hats would be the coefficients that are going to be estimated with the regression model. N would be the number of observations, and I would be any of the observations. So I would be equal to from 1 to n. So we have n observations, but if we refer to I, this means any of the 1 through n observations. So here the residual is u hat equals y minus y hat. Here, the residual is the actual value minus the predicted or the fitted value for the dependent variable. And again, we can have a population with all of the objects that we're interested in modeling and a sample from which we have the data. So if we refer to the population, we would talk about the parameter beta and the error term u. If we refer to sample, the coefficient beta hat and the residual would be u hat. So what is the interpretation of the coefficients? Taking the derivative, we have beta j hat equals change in y over change in xj, where again, this xj could be any of the independent variables, and beta j hat, this could be any of the coefficients that refers to this variable. So the interpretation is that beta hat j measures by how much the dependent variable changes when the independent variable xj increases by 1 unit when holding other factor fixed. So here it is also assumed that the unobservable factors do not change if the independent variable changes. So the change in u over change in xj is equal to 0. So here's an example of a regression model. So here we have multiple regression model explaining how the wage of workers is explained by their education, experience, and the tenure that they have in the company. So the multiple regression model would be wage equals beta 0 plus beta 1 times education plus beta 1 times plus beta 2 times experience plus beta 3 times tenure plus u. So here y is wage and the x variables are education, experience, and tenure. Wage is measured in dollars per hour, education in years, experience in years, and tenure in this company is how many years you've been with the company. The estimated equation for the predicted value of wage is wage hat equals beta 0 hat plus beta 1 hat times education plus beta 2 hat times experience plus beta 3 hat times tenure. So notice again is that the regression model, the one for the population, has the error term at the end, and none of the parameters here have hats. Here, after we estimate the equation with the sample data, we no longer have the error term. We have the predicted value here, and all of the coefficients have hats on them. So here the residual u hat would be wage minus wage hat. And we will estimate this regression model to find the coefficients, and beta 1 hat would measure the change in wage associated with one more year of education, holding other factors fixed. So here's the estimated equation and the interpretation. A computer software such as Stata has given us the coefficients, and I have put them right here. So because of how the dependent and independent variables are measured, the interpretation of the beta 1 coefficient here would be the hourly wage increases by 60 cents for each additional year of education. Here, the hourly wage would increase by 2 cents for each additional year of experience, holding other factors fixed. And for tenure, we have that the hourly wage would increase by 17 cents for each additional year of tenure in the company, holding other factors fixed. The interpretation of the intercept is that if all of the regressors are 0, then the person's wage would be minus $2.87. However, since no one in the sample has 0 for all the regressors, this would be not a value that anyone would have. So let me show you the same example. Now it's coming as data output. Any computer software such as R or SAS would give you a similar kind of regression output. So after you estimate the equation, regress, you put the dependent and independent variables here. This is the regression output that you will get. And the coefficients of 0.6, 0.02, and 0.17 is exactly what I showed you on the previous slide. So this is an alternative way to kind of show the coefficients and for you to obtain the coefficients from the regression program and then put it into a table. So here is how we economists like to present the regression output. So we put it like that in a table. And on top, we say what kind of model we have. So I have regression with one independent variable. Here is I have regression with two independent variables and a regression with three independent variables. So in all of our cases, wage is the dependent variable in these models. So that is usually put on the top of the table as uh, denoting the columns. And the independent variables are put here: education, experience, tenure, and then we have the constant. So here, if education is the only independent variable included, that would be the coefficient. In the model that has two independent variables, this is education and experience, and these are their coefficients. And in the model with three independent variables, these would be the coefficients for education, experience, and tenure. And if you notice carefully, these are exactly the coefficients that are on the previous two slides. So that's how they would be denoted in a table. So here again, when education increases by 1 year, wage would increase by 60 cents, holding other factors fixed. And notice that if we estimate different models with different number of independent variables, that coefficient of education changes slightly from a model to model, which means that the other independent variables also influence the value of this coefficient. So now let's move toward the derivation of the OLS estimates. So how do we do that? So for a regression model that we have here as a function of the independent variables, we need to estimate the regression equation y hat represented by the coefficients times the independent variables. So we are going to find these coefficients beta hats by looking at the residual, and the residual again is u hat. That's the difference between the actual and the predicted value of the dependent variable. So if you look at the predicted value of the dependent variable, I can substitute instead of this, I can substitute this expression, and this is what is done here. So now for the residuals, we have an expression that has all of the actual values of the dependent and independent variables, and we need to estimate these coefficients here. So we do that by obtaining a random sample of data that have n observations. And here we have xij, where I equals from 1 to n is the observation, and j equals from 1 to k is the index for the independent variable. So again, here we have k independent variables, we have one dependent variable, and I is how many observations we have here. That number is n. So once we have the sample, the goal is to obtain as good fit as possible of the estimated regression equation, and we do so by minimizing the sum of squared residuals. So here in this function, we have minimizing the sum of squared residuals. So all of the words are in this formula: minimizing the sum of squared residuals. And so because the residuals are already the expression that I showed you on the previous slide, we can substitute this expression here and minimize this function. So as part of the optimization process here, we obtain the coefficients beta hat. And I showed you what the formulas look like with a simple regression, but these formulas are a bit more complicated for multiple regressions, so we are not going to show the formulas here. But these coefficients are obtained with the statistical programs. Here, OLS refers to, again, ordinary least squares, and uh, it's ordinary because it's not weighted and it's the regular least squares. Least because we're minimizing, and squares because we're minimizing those sum of squared residuals. So what are some of the desirable properties of these OLS estimators? The first one is that the sample average of the dependent and independent variable on the regression line. So here we have y bar, that's the average of the dependent variable, and x1 bar and x2 bar, and so on. These are actually the independent variables that we have here. So the residuals sum up to 0. So note that the sum of the squared residuals are minimized, but the residuals ui hat, they still sum up to 0. So this means that we have all of the residuals across all of the x variables, they have to sum up to 0. We also have as a property here that the summation of xij times u hat I, that summation is equal to 0. So what this means is that covariance of x, the independent variable, j, and u hat, the residual, is 0. So again, we see no relationship between the independent variable and the residual, which means for any given x, we would see that we have uh, the u's would be basically summing up to 0. So now let me show you what partialing out means. Partialing out shows an alternative way to obtain the regression coefficient. So here for the population regression model, we have that would be the population regression model. So instead of estimating this model, what we can do is first regress the independent variable on all other independent variables. So here we would be regressing x1 on the other variables x2 and x3. So notice that now, for the first time, we see that an independent variable serves as a dependent variable for this regression. And these are the parameters alpha 0, alpha 2, and alpha 3 are the parameters for this new model, and this E is the error term for this new model. So we can estimate this model and get the residuals. So this is the error term E. The residuals would be E hat, which is the dependent variable minus the predicted value of the same dependent variable. And in our case, the dependent variable was x1 minus its predicted value, x1 hat. So these are the residuals from the regression above, showing the part of the independent variable that's not explained by the other variables, right? So this is the part here that we can explain with the regression, but the residuals is the part that we're not explaining with the regression. So now we can run the regression of our dependent variable y on the residuals from this regression. So here we can run y, a regression of the dependent variable, on these E hat residuals from the previous regression right here. And these are the parameters that we're going to get. This is a gamma 0 new parameter. That's a new error term. And beta 1, this coefficient here, would actually happen to be exactly this coefficient that we have on the x1 variable. So how to interpret this is this beta 1 hat coefficient shows the relationship between y and x1 that is not explained by the other variables. That's why we're adding holding everything else fixed when we're interpreting the coefficients. And again, here we can either obtain the coefficient here by estimating this regression and saying that we're holding everything else constant, or we can first estimate the regression of this variable on all the other variables, get the residuals. So basically we would only have the here the residuals that from the regression of x1 that is not being explained by these other variables, and regress the dependent variable on them. That would actually lead to the same coefficient. So let me show you the example here. So we can have the regression of wage on education, experience, and tenure. So this is our standard equation that we've estimated, and I've shown you the results before. So now let's estimate a regression of education being the dependent variable. So our independent variable here becomes the dependent variable, the education regressed on experience and tenure on the other two independent variables. So these are the coefficients from that. So from this regression that we estimated, we would be calculating the regression E hat, the residual E hat, and that residual E hat here would now serve as the independent variable. If we regress wage on this residual, that will be the coefficient. So notice that there are no other independent variables here, just this one. And that coefficient is exactly the same as the coefficient here. So that is not the coincidence. This is exactly what partialing out means. Um, so again, that coefficient here would mean that if education increases by 1 year, wage would increase by 60 cents, holding everything else fixed because again, um, we have accounted for everything else in the model. So now let's switch gears and talk about goodness of fit measures, and this will be the R squared and the adjusted R squared. So what is R squared? First of all, remember that SST equals SSE plus SSR. In other words, the total sum of squares equals the explained sum of squares plus the residual sum of squares. And the R squared or R squared written like that is the SSE divided by SST. So what proportion of the variation we can explain with the regression divided by the total variation that of the dependent variable. That is also equal to 1 minus SSR, the sum squares residuals divided by SST. So again, R squared is equal to the explained sum of squares divided by the total sum of squares. And it measures the proportion of the total variation that is explained by the regression. The rest would be due to error. And that's why R squared is a goodness of fit measure. So how good is the model to be able to explain the variation that we see in the dependent variable? So an R square of 0.7 would be interpreted as 70% of the variation is explained by the regression and the rest is due to error. And an R squared of greater than 0.25 is considered a good fit. So one problem that we have for the R squared is that it always increases when an additional regressor is added because the SST, the total sum of squares, is the same, but the SSE would increase when we add a new regressor. So in order to fix this problem, we can calculate the adjusted R squared. And the adjusted R squared would be an R squared that has been adjusted for the number of regressors in the model. So the adjusted R squared will increase only if the new regressor improves the model. So recall from the previous slide that we have the R squared equals 1 minus the sum of squared for the residuals divided by the sum of squares total. The adjusted R square, on the other hand, this formula is still the same up to here, but here we would be dividing by n minus k minus 1, and here we would be dividing by n minus 1. So n would be the number of observations and k is the number of independent variables. And what we are doing here is basically if we continue to add too many independent variables, this is the penalty here that we're going to have for the adjusted R squared. So that would be pulling down or lowering the adjusted R squared if we include more independent variables. So the adjusted R squared can also be explained with the R squared. So this would be the relationship, noticing that this expression here is exactly the 1 minus the 1 minus R squared. So that is the relationship between the adjusted R squared and r squared. So as the number of regressors k increases, the adjusted r squared would be penalized. Again, if you look at this expression, when k increases, that would lead to a lower value for the adjusted r square. But when adding more regressors, the adjusted r square may increase, but also may decrease or even get negative. And that's an empirical question of how much a new variable contributes to the model. Um, so the rule of thumb is if you add a variable and that increases the adjusted r square, you can keep it. But if it doesn't increase the adjusted r squared, you can basically drop it from the model. And the rule is to choose a model with the higher adjusted r squared when deciding when to keep a variable or not in the model. Basically, that's one of the rules is if a variable increases the adjusted r squares, we can keep it, and if not, if it lowers it, we can drop it from the model. So let me show you where the adjusted r squared is found on the output and its calculations. So this is the so-called ANOVA table in the regression output. And here we have the sum of squares for the model, also the explained sum of squares, the sum of square for the residual, and the sum of square total. And the r squared is already calculated and given to us as part of the output, and the adjusted r squared is also calculated and given to us as the output. But let's go ahead and calculate them manually. So here the r squared, the formula is SSE, or the explained sum of squares, or same as SS model, divided by SS total. And so we would be dividing the 2194 number by the 7160 for the total. And that is also 1 minus the SSR divided by SST. So it's the same as 1 minus 4966 divided by 7160. Or that is the point uh, 306 that we see exactly right here. So that is how the r squared is calculated. For the adjusted r square, we use the following formula. And again, we substitute the SSR is this number, the SST is this number, n minus k minus 1. Here we have three independent variables, and the number of observations is 526. So this is n. So n minus 1 will be 525. So this is what I've put here. And n minus 1 minus k would be the 526 minus 3 independent variables minus 1, and that would be the 522. These two numbers, you can find that's the number here, and this 525 is that's the number here. So the degrees of freedom for the model, that is basically k, the number of independent variables, and this is n minus k minus 1, and this is the n minus 1. So to calculate the adjusted r squares, you calculate this expression and you find that that is 0.302, and that exactly is given to you as the adjusted r square, which could also be calculated manually. And so how you interpret that is that 30% of the variation in wage is explained by the regression and the rest is due to error. So let me provide an example of the r squared and adjusted r squared and what happens when we add more regressors. So this is the same example that we had before, same dependent variable of wage. And here we have one independent variable, which is education. Here we have two independent variables, education and experience. And here we have the model with three independent variables, education, experience, and tenure. And these are the coefficients and the standard errors. These are the sum of squares total. And so these are the numbers and the calculations that I showed you before. The SSE for the explained or the model, that's the SST. And these are the r squared and adjusted r squared that we calculated on the previous slide. Now notice that if we have fewer variables, the SST is still the same. So what happened? Because the sum of squares total, that's the variation of the dependent variable, that's the y minus y bar squared, the summation of that. So that would not change regardless of our model. So that's why that's the same. But one thing that happens is that what we can explain with the model always increases when we add a new variable. That's the property, because that new variable would pick up more and more of the variation and would be able to explain more. And so this is why the r squared actually, if you divide this number by this one, this is the r square, SSE divided by SST, the r square will always increase when we add more independent variables. However, whether the adjusted r square increases or decreases, this is basically an empirical question. And in our example here, it so happens that the adjusted r square, as we're calculating this, also happens to increase, but that's not always the case. Like the adjusted r square may increase or decrease depending on if the variable contributes enough in being able to explain uh, the variation in the dependent variable. So here, the most desirable model is the one that has the adjusted r squared of zero point 0.3. And so based on the criteria of the adjusted r square, we would pick the model that has three regressors. So here's how we can use the r squared or adjusted r squared for models that are non-nested. So again, this means that one cannot be directly obtained from the other by just restricting the coefficient to equal to 0, like it was in the previous slide, we had nested models. So here we have the example of salary being the dependent variable. These are the salaries of the CEOs, and here log salaries are the dependent variables. We have return on equities, one of our independent variables across all of the models. And then we have sales of the company, either measured as levels or as log sales in the other two models. So here we have the all combinations of linear, linear log, log linear, or log log models, depending on whether the dependent variable is logged or not and the independent variables are logged or not. So what happens now with the r squared and adjusted r squared? So notice that the SST is the same for the for the models that have the dependent variable as salary. So this is the same because the total variation in the dependent variable is the same across both models. But how much does this model explain? This is the variation that is here, and how much this model explains, that's the variation. And if we divide these two numbers, that will be the r squared. The adjusted r squared accounts for the number of independent variables, so we get these two numbers. So using the criteria of using adjusted r squares of deciding whether or not a variable should be or shouldn't be in the model, this one gives a higher uh, a better fit than this one. So based on this criteria, we should be using this model here. Now notice that the sum of squares total changed to 67 when we have the dependent variable measured in log salary rather than in salary. So we have a lot less variation in the dependent variable because logs basically transform the original variable into logarithms. So here, if we divide the SSE by the SST, these are the r squared and then the adjusted r squared. So in this case, it so happened that this model again has a higher adjusted r squared. So this means that again, if we are using the log of sales rather than the sales, this gives you a higher adjusted r squared. So using this criteria, we should be using this model with the log of sales. Using this criteria, again, the adjusted R square, we should be using the model with logs. Now, comparing amongst all of the adjusted R squared, this one is the highest adjusted R square amongst all the models. And so only using this criteria, we would conclude that the last model is preferred because it has the highest adjusted R square of 275. Now, there are other criteria in deciding whether you log or not variables and so forth, and what to include in the model, but this is one of the criterias, is what happens to the adjusted R squared. Now, moving on with very, very important assumptions. These are called the Gauss Markov assumptions. And these are the standard assumptions for the linear regression model. They apply for the simple as well as the multiple regression model. So these are very quickly, and then I'll explain them slowly. Linearity in parameters, random sampling, no perfect collinearity, zero conditional mean, also called exogeneity. This is when the regressors are not correlated with the error term, and homoscedasticity, which is the variance of the error term being constant. So let's go over them slowly. Assumption one is linearity in parameters, and this is the model that I showed you on the first slide. And so notice that the relationship between the dependent and independent variables is linear in the population. What that means is that these beta 1, beta 2, and beta k parameters enter linearly between the independent variables and the dependent variable. Now, that does not preclude x2, for example, to be log of sales, or x2 to be the square of the x1 variable. So this one here to be x1 squared, or interactions of variables such as this variable here could be x1 times x2, but the beta parameters are linear. So again, the variables could be anything that they want, because to a computer software like Stata, that's just a bunch of numbers, but the parameters need to be linear. The second assumption is random sampling. So here is when the data are random sample drawn from the population, and each observation here has equal probability of being selected. So we're not oversampling any of the observations from the population. And each observation would follow the population equation above. Assumption 3 is no perfect collinearity. So what this means is that none of the independent variables are constant, and there are no exact relationships amongst them. So let's go over this carefully. An independent variable cannot be a constant because it will be collinear with the constant or the intercept in the model. So because we already have one constant in the model, we cannot have a second an independent variable that does not vary for its observations. So each of the independent variables needs to have some variation in it. An independent variable also cannot be a perfect linear combination of the other independent variables. That would be called perfect collinearity, and it must be dropped from the model. So now here's a note that independent variables can still be highly correlated with each other. That's called multicollinearity, which is not a violation of this assumption, but multicollinearity is also problematic, as I will show you later on. So when does this no perfect collinearity cause trouble? Well, if say the independent variables are shares that sum up to 100, say the proportion of income spent on food and proportion on income not spent on food. For example, for one person it could be 20% spent on food, 80% not spent on food. For another person could be 30% spent on food, 70% not spent on food. But these two variables would sum up to 100% for each of the individual. And that 100% would be collinear with the constants. So such two variables cannot be included in the model. So one of them has to be dropped. So we can include the proportion of income that is spent on food, but drop the other one from the model. On the other hand, if you measure how many dollars you spend on food versus how many dollars you do not spend on food, such as you can spend $200 per month on food versus $800 not spent on food. Another person could have say $300 on food, but it could have 1,500 not spent on food because these two variables don't sum up to any number in particular, but to a total income that would vary across the individuals. These two variables would not cause a problem and they could both be kept in the model. Now, let me give you an example of perfect collinearity. This is when we have two variables, independent variables, have a perfect re relationship with each other. So here's a model where we have female, whether or not a person is female, included in the regression. So we have wage equals beta 0 plus beta 1 times education plus beta 2 times female plus use. So this female would be an indicator variable, a 0, 1 variable. So if we try to have a model that has both female right here and male as a dependent variable, where this male would be equal to 1 minus female. So notice that male plus female sum up to 1 because in the sample you have to be either male or female. So if it's 0 for female, it would be 1 for male and vice versa. So this model that we have here cannot be estimated because male and female are perfectly collinear. So if you actually try to run this model in, say, Stata, it would actually tell you that this model cannot be estimated and it would drop one of the two variables for you. So what would be the solution? So you can drop the collinear variable male, or you could drop the collinear variable female. One of them has to be dropped. Or on the other hand, if you want to keep both male and female in the regression model, then you can drop the constant. But this is not commonly used. So here's the perfect collinearity example. So here we have a model with female, so that's the regular model, where wage is the dependent variable, education and female is the independent variable. And if you try to run a model where female and male are both included, it includes a coefficient for O, standing for omitted variable dot male. So it omits it and it cannot give you the coefficient. Theta would not give you the coefficient because it's perfectly collinear. So alternatively, you can estimate a model where it has both female and male here, but notice how for the first time that we see a model without the constant. So now again, this is not very commonly used to keep all of the collinear variables. It's typically a better practice to like drop one of the variables that is collinear. So none of the shares sum up to 100%, or you can't have both. If it's dummy variables, you cannot have both male or female, or if it's categories like whether a person is freshman or sophomore, junior or senior, you have to skip one of these categories and not include it in the model. Otherwise, we would have perfect collinearity. So now let's talk about a related concept, which is multicollinearity. So this is not the perfect collinearity where it's an exact relationship, but it's a relationship between two or more independent variables that are highly linearly related with each other or correlated with each other. So when they are not perfectly collinear, that's not a violation of assumption 3 that we have here, but it's still not a good idea to include such variables in the model because they're almost identical to the other variables in the model, and that causes problems with the estimation. So how can we check for multicollinearity? We can use the variance inflation factors, or VIF. And VIF is calculated for, say, J, for a independent variable J or coefficient J as 1 divided by 1 minus the R squared J. This R squared J is the R squared from a regression of J on all the other independent variables. So if we regress, say if we are interested in what is the VIA for the third independent variable, we would regress the third one on the first and the second. So here, higher r squared for the third variable would mean that it is well explained by the other independent variables. And from the formula above, if we have higher r squared, because it comes with a negative sign, but it's also in the denominator, that would mean the higher r squared j would lead to higher VIF j. So that would be higher. So a rule of thumb is to drop a variable xj if the VIF for this variable j is greater than 10, which means that the r squared j would be greater than 0.9. So if this is greater than 0.9, this will be less than 0.1, and so that's how this VIF would be greater than 10. So this means that this variable would be well explained by the other variables in the model. Think about what this r square here means. That is basically how well the rest of the variables explain this variable. Well, if the rest of the variables explain more of the 90% of the variation for this variable, then this variable is kind of redundant in the model and should not be included in the model. So a side note to point here is that VIF equals 1 for simple regression because there are no other variables, so this expression would be 0, so the VIF would be 1. I also would like to talk here about the fact that some people use correlation coefficients to also decide whether to keep or drop variables from the model. And the rule of thumb is that the correlation coefficient above 0.9 with another variable would result in this variable being dropped from the model. But in general, it's better to use the VIF for multicollinearity because it accounts for relationships among all independent variables, whereas the correlation coefficient only looks into correlation between two variables. So let me show you an example of multicollinearity. So here we have a model of how the test scores of a student depend on parents' average education and whether parents went to school and graduate school. Now, looking at these independent variables, parents' average education and whether they went to school or graduate school, they would be very highly correlated. Their average education will be definitely higher when they went to college and to graduate school. So here we can first find the correlation between two variables at a time. So this is a table of correlations. So the correlation of a variable with itself is 1. The correlation of average education, whether they went to graduate school, is 0.79, and average education, whether they went to college, is 0.81. So these are very, very high correlations among this variable and these two variables. And this is a much lower actually correlation coefficient here. So we already have an indication that these variables are very much correlated here. So here's what we can do. We can estimate a model that the test score is the dependent variable and all three are the independent variable. Test score is the dependent variable with only these two being an independent variable. And we can estimate a model where test score is the dependent variable, but parents' average education is only one independent variable. So when we estimate a model that has multicollinearity with the three independent variables and we calculate VIF, so these numbers here are actually the VIFs. If we see that this VIF here for parents' education is actually a number above 10, and we said that 10 is the cutoff for this variable. So here we have the other VIFs are definitely not a problem. And here we have the VIF if we have one independent variable that is equal to 1. So these two models are fine because the VIFs are less than 10. But this model is problematic because the VIF for this variable is above 10, and we definitely need to drop this variable average education. It's better to estimate either this model or this model. So here are the estimated models when we have the model with multicollinearity, and here's the models without it. So the model that has multicollinearity is that all of the three variables are included in the regression, even though they're very highly correlated with each other. And here is only a model with these two variables, and here's another model with just this variable. So notice that the coefficients here, this coefficient is very different from this one, and this coefficient is very different from this coefficient. Actually, this one even changed sign, went from a negative to a positive coefficient. So when we have a problem of multicollinearity here, we could actually wrongly conclude that if their parents went to college, the students' test scores are actually lower. And again, this is a wrong conclusion that we would have. So here, what we are advising in this case is because the parents' average education was very highly collinear, we should drop this variable and use this model instead. So that would be a lot better model to use. Alternatively, we can just use this variable, but then we should not be including these other two variables. Another point to note here is that actually the standard errors are higher for the models that have collinearity. So the standard error here is much higher than the standard error here. And the standard error here is higher than this one. And this standard error is also higher than this one. So that's also what happens when we have a model with multicollinearity. That would lead to higher standard errors. Basically, that's not a desirable feature. Okay, so moving on, assumption number 4 is a zero conditional mean or exogeneity. So here we have the expected value of u given all the various x's are equal to 0. So the expected value of the error term u given the independent variables x is 0. What that means is that the expected value of the error must not differ based on the values of the independent variables. So when we have more independent variables, this assumption would be more likely to hold because there are fewer unobservable factors that could end up in the error term and affect this expression. So here, any independent variable that's correlated with the error term, that would be called endogenous, and endogeneity would be a violation of this assumption. And independent variables that are not correlated with the error term, they would be called exogenous, and this assumption would hold if all of the independent variables are exogenous. So again, expected value of u given x equals 0, so we want independence between u and x. If this expected value is not equal to 0, we would basically have endogeneity in violation of this assumption. So let me show you an example of zero conditional mean. So here we're back to the model of wage equals beta 0 plus beta 1 times education plus beta 2 times female plus u. In this example of wage and education, one other variable that we have not included is the person's ability. And so the person's ability also affects the wage, but if it's not part of the independent variables here in the model, this means it has ended up in the error term and it's an unobserved variable. And so one of the issues is that when ability is higher, this error term would be higher. And so basically our variable here, education, would also likely be higher. And so that would be a violation of the assumption that the error term, the expected value of the error term given education, needs to be 0, because again, educated people would be more likely to also have higher ability. And so when education would increase, one of the problems is that we cannot hold uh, this error term unchanged, because ability is in it, and ability would also be increasing here. So let me show you an example. So this is exogeneity or zero conditional mean. If we look at residuals here, we would have that for any value of x here for education, basically if we sum up these residuals for each x, they would sum up to 0. So however much we have above the line of 0, we would have below the line of 0. This is an example here that I made up, but this would be a case where, say, if we have endogeneity for higher value of education, we would actually have higher residuals here. And for lower value of x, we would have lower residuals. So again, this is a violation of this assumption of zero conditional mean, and we would have endogeneity of education. So under the Gauss Markov assumptions 1 through 4, so these are the linearity, random sampling, no perfect collinearity, and zero conditional mean. Uh, this leads to the unbiasedness of the OLS estimators. So what that means is that the expected value of beta j hat would be equal to beta j. So the expected value of the sample coefficient beta would be the population parameter beta. And so here j equals from 0 to k. So we're going through all of the coefficients that we're estimating. And so what we're saying here is that if we estimate the regression model with many random samples, the average of these coefficients would be the population parameter. So again, in any given sample, the coefficient may be very different from the population parameter, which we do not know. We will never know, and we're trying to estimate. But on average, if we have many different samples, we would be hitting the population parameter. That's what we would get as the average value of these sample coefficients. So this means for the OLS estimators to be unbiased, that the expected value of the sample coefficient is the population parameter. So now let's talk about omitted variable bias. So omitted variable is a variable that is omitted from the model, which means it's not part of the model. And what that means is that if we have an omitted variable like that, that would lead to biased coefficients. So let me show you how that's the case. So suppose that the true population regression model is this one. So the dependent variable is explained by x1 and x2. And there's an error term. So what we need to estimate is y hat based on x1 and x2. However, suppose that we estimate a misspecified model, that is a y tilde equals beta 0 tilde plus beta 1 tilde times x1, where x2 is the omitted variable from the model. So as you notice in this model, I do not have x2 in the model. So that is why this model is misspecified, because it's not like the correctly specified model here that includes x2 in it. I do not have x2 in here. So that's a problem, because if x1 and x2 are correlated, there will be a relationship between them. So x2 would be related to x1 via this regression. So these are new parameters here, delta 0 and delta 1, and that's our new error term. But here's a regression that did not go away when we missed to include x2 in the model. So if I just substitute, this is an expression for x2 in terms of x1. If I substitute this expression, back into my original regression model here, I just put the expression here for beta 2. That's what we're going to find. Y equals this expression, and here I have substituted exactly the expression for x2. That's the expression for x2. And now I can open the parentheses, and I can regroup like this intercept with this intercept, this coefficient with these coefficients here, and so forth. And that's what I will have when I have an intercept. This is my x1 variable, and this is my new error term. So effectively, if the true model incorporates x2, but I forget to include it and I estimate a model without x2, I'm effectively estimating the model here, where all of these other coefficients are going to be still in the model, even though x2 is not included. So the coefficient that would be estimated for x1 is this coefficient here. It's not going to be beta 1 as we saw before. So when x2 is omitted, this will be the estimated coefficient for beta 1, and it will be biased. So remember this expression for the x1 coefficient, and let's talk more about it. So an unbiased coefficient is when the expected value of the coefficient beta 1 hat is beta 1, the population parameter. But this coefficient is biased because the expected value of it, the beta 1 tilde, would be beta 1 plus beta 2 times delta 1. That's the expression that we had in the parentheses before the x1 variable on the previous slide. So this beta 2 times delta 1, that one is the bias. This one is the true coefficient, but this one is the bias. So now, when we have an omitted variable, the coefficient will not be biased. How? Well, if this bias is equal to 0. That bias could be equal to 0 in two cases. First, beta 2 could be equal to 0. So if beta 2 is equal to 0, looking at the population regression model, if beta 2 equal to 0, this means that x2 does not belong in the model, or x2 is irrelevant. So again, if the population parameter is 0 here, it means that x2 does not belong in the model. Another way in which this bias would be equal to 0 is if this delta 1 is equal to 0. If delta 1 is equal to 0, if we look at the expression, that a regression model that we estimated that expresses x2 in terms of x1, this is the delta 1 being equal to 0. So that means that x2 and x1 are not correlated at all. So x2 and x1 do not move together. So in other words, to summarize these two bullet points here is that if the omitted variable is irrelevant, so its coefficient is equal to 0, or it's uncorrelated with the one that remains in the model, there will be no omitted variable bias. So again, that is the problem of when you have an omitted variable. Basically, if a variable is in the model, but you don't include it in the model, the problem is that what's remained in the model and the other variable would have a bias coefficient. And that's a really bad outcome that we have. So let me show you an example. Suppose that the true population model is wage equals education. Wage depends on education and ability. So higher education would result in higher wages, and higher ability would result to higher wages. Well, suppose that for some reason we cannot measure and we don't have the variable ability. So even though that's the true population regression model, if I cannot find ability, or we didn't measure it, or it's not included in the data set, well, we're not going to have it in our model. So if instead we estimate a misspecified model of wage depends on education, so these are some new parameters and new error term, then we would have this ability being the omitted variable from this model, because ability is not here. But ability and education are correlated, and there will be a relationship between them. So ability would depend on education. Why? Because more educated people are more able in general. If we substitute this equation into the above equation here for ability, here we have wage equals, and I've replaced ability with the equation that I have above. I open the parenthesis. This will be the coefficient that we have here on education. So now notice that in this model, if I miss ability, its coefficients are still in the model, even though I don't have the variable. And so this coefficient here would be biased because the coefficient on education is no longer beta 1. That would be an unbiased coefficient of beta 1. But I have an addition to beta 1, and that's the bias here. And this bias is beta 2, which is the coefficient of ability. How does ability affect wage directly? And it's the delta 1. It's basically the relationship between education and ability. That's what this bias here is equal to. So let's estimate this model and just see the coefficients in practice. Here's how we've estimated the model. So here we have wage being the dependent variable, education and ability being our independent variables. So in this case, I actually do have data on ability and I can include it in the model. So these are the estimated coefficients for education and ability. These are the correctly specified model. So if education increases by 1 year, we would have the wage would increase by $1.15. That's how you interpret this coefficient. But we also notice that when ability increases, that also increases the wages as well. So now suppose that instead of estimating the correctly specified model, we estimate a model here with education, but ability is skipped. You see, like we did not include ability in the model. So what would happen here is that we have now a model that we omitted ability and the coefficient on education is 1.39. So the way we would interpret this coefficient is that if education increases by 1 year, our wage would increase by $1.39. So notice how now we are overstating the effect of education on wages from what we had before. Now we're going to say that education more strongly influences wages. Well, let's estimate the model of ability and education. So we flip the case here where ability is the dependent variable and education here is the independent variable, and that is the coefficient on that. So we see that actually education and ability are related to each other. So when education increases, uh, ability definitely increases as well. So let's talk about the size of this bias. Well, um, this this coefficient here in the model with the omitted variable, that is the bias coefficient. And so this coefficient of 1.39, if you want to break it down, that is the original coefficient, the 1.15, plus the size of the bias, or it's the beta 1 hat plus beta 2 hat times delta 1 hat. So let's find these coefficients here. The beta 1 hat, that's the coefficient on education. And so this is this coefficient here. So this is the original coefficient. Plus we have beta 2 hat, that's the coefficient on ability. Plus we have delta 1 hat, that's that coefficient here of the relationship between ability and education. So if we actually do the multiplication, that here is the size of the bias. So here we would have that 24 cents would be a bias. So in this model here with the omitted variable, we're wrongly saying that if education increases by 1 year, salary would increase by 1.39 dollars, because 24 cents of that is actually due to the ability. And how does it enter? It enters through its own coefficient and its relationship with the other variable that is still in the model. And so that again, this coefficient here is overstated because of the bias. Another way to think about why this coefficient is biased and it overstates the effect of education on wage is because if ability is not included as a separate independent variable, it's in the error term. So when you increase education by 1 year, the error would also increase because the ability in that error would increase, and that's what it overstates this coefficient. Okay, so here I would show you a different example just to show you that the bias does not always have to be positive. It could be negative. It's an empirical question. So here we had the same model, but instead of just having education and ability, I have education and experience. So going through it very quickly, if we estimate the correctly specified model, these are the coefficients. And here is the model where we skip experience if experience really belongs in the model. And this is a model where experience is regressed on education, and that's that coefficient. So repeating from what I had on the previous slide, this coefficient that we have here is the original coefficient, 1.94. So this coefficient is the original coefficient plus this is this coefficient times this coefficient with a negative sign. So here we have um, actually negative bias. So the negative bias is of 56 cents. So now instead of saying that education increases wages by $1.94 for each additional year of education, we're saying that it increases by $1.39. And that is coming from the negative experience between education and experience. So here we have that actually more educated people have less experience, and that's why this bias is negative. So in this case, again, we would have this coefficient with the omitted variable. In the case of the model with the omitted variable would be underestimated or lower. So again, these are very bad outcomes of if a variable truly belongs in the model, but you omit it in the model from the model, you don't have data or something for it, because what happens is that biases the rest of the coefficients, and so they're no longer unbiased. So now we can have the reverse case of where we are including irrelevant variables in the model. So suppose that the true population regression model is where the dependent variable y depends on x1 and x2, but instead we estimate a misspecified model where we include a variable that does not belong in the model. So for example, you could think in the example of how wage depends on education, experience, and ability. You could put an irrelevant variable there, such as how tall a person is. How tall a person is should not affect your wage. So therefore, such variable x3 would be an irrelevant variable. So in this case, in the population regression model, the expected value of the beta 3 hat coefficient would be the beta 3 parameter, and that would be equal to 0 because this variable is not included, right? We shouldn't have how tall a person is affect education. So in this case, an irrelevant variable would not cause bias because that coefficient here is equal to 0. And we talked about this before in the case of omitted variable bias. Another thing to mention here is that even though an irrelevant variable does not cause bias, it still increases the sampling variance, so it's still not a good idea to include irrelevant variables in the model. Now, assumption 5 is homoscedasticity. And homoscedasticity is when the variance of the error term, given all the independent variable, is sigma squared, is constant. So the variance of the error term does not depend on the independent variable. Heteroscedasticity is when the variance of this error term, given the independent variables, does not equal to sigma square, or it's not constant. So let me show you examples of homoscedasticity and heteroscedasticity. If we estimate the model here of wage on experience, education, and so forth, and plot the residuals, here we have the residuals U hat against experience. And one thing we're finding is that for each value of experience, the variance of that does not seem to increase or decrease or change much as we go along the x value. However, for our independent variable education, you see like how for low values of education, the residuals are, the variance is small, but for high values of education, the residuals are high. So if we see something like that, this means an increasing variance. And so later on, we would show how to correct for this heteroscedasticity. But for now, assumption 5 is homoscedasticity. We assume this case and not this case where we have increasing variance here or variance not being constant uh, of the error term based on the values of the independent variable. Okay, let's talk about the variances of the OLS estimators. So recall with simple regression, that was the formula for the variance of the coefficient beta 1 is equal to sigma squared divided by SSTX. Here with multiple regression, we would have variance of beta hat j. So for variable xj, this will be the coefficient, is sigma squared divided by SST for the variable xj times 1 minus the r squared j. So let's go over all of these terms and explain them. What does that mean for the variance of a coefficient to be equal to? The first term to explain here is SSTJ, and so that is basically the total sampling variance of the variable xj. So we have the variable xj minus the mean for xj. So this is basically the variance of the xj variable. Um, so high variance of the regressor would lead to lower variance of the coefficients. So the higher this value, because it's in the denominator, we would have a lower value for the variance of the coefficient. So again, we want as much sampling variation in the x variable that would lead to less variance of the coefficient. That would be a good uh, desirable uh, desirable thing. So r squared j, this will be the r squared from a regression of the variable xj on all of the other independent variables. So high r squared means that this regressor xj is very well explained by the other regressors, which means multicollinearity, and will have higher variance of its coefficient. So again, if we have a higher value here, that's a negative sign, but it's in the denominator, we would have a higher variance. So again, if we have a variable, xj, let's say the third variable, if that variable is very, very well explained by the other variables in the model, say by x1 and x2, we would have that its coefficient would have a lot of variance. So the standard error would be very high for this coefficient. So again, that's not a very good property here, not very desirable. And the last term here is sigma squared. That's the variance of the error term. And so high variance of the error term here would lead to high variance in the coefficients. So again, the more variance we have for the error term, that would of course lead to variance in the coefficients. So to summarize this, estimators that have lower variance are also called more precise. They're desirable. So that would mean high variance in the independent variable, low r squared for xj, so less multicollinearity, and low variance of the error term would be desirable. Again, overall, this is the formula for the variance of the coefficients, and it depends on the variance of the error term, the variance of the regressor, and uh, basically this r squared j, which shows how does this variable j is explained by the other regressors. So now we do not know the variance of the error term, sigma squared, but we can estimate it as the variance of the residuals and correct it for the numbers of regressors. So here we would have that sigma hat squared would be equal to the summation of the residuals divided by n minus k minus 1. That's called the degrees of freedom, and this is the number of observations minus the number of regressors minus 1. And that would be an estimator for the variance of the error term. So the Gauss Markov assumptions from 1 to 5 mean that the expected value of sigma hat squared would be equal to sigma squared. So this means that we don't know the true population variance of the error term, but we can estimate with what we have. This is the variance of the residuals coming from the sample, and that would be an unbiased estimate. So plugging in this expression here in the variance formula, so notice that the standard error of the regression coefficient is the square root of the variance. And this was the variance formula that I had before in the previous slide, only that I have replaced here sigma squared with a hat coming from the regression. This is the estimation coming from the regression. So here, the standard errors of a coefficient would measure how precisely these coefficients are calculated. We also see the standard errors, they're included in the regression output. And we would be interpreting these later on. So now let's talk about what happens when we have misspecified models and we forget to include a variable in the model. So this would look similar to the omitted variable bias example. So suppose that we have the true population regression model. Y depends on x1 and x2. And so we need to estimate a regression equation that is y hat depending on x1 and x2. But instead, we estimate a misspecified model where y only depends on x1. And so x2 would be the omitted variable. So what happens to the variance of this beta 1 hat here versus this one here? So if we look at the variance of beta 1 tilde here, that is the variance that we have in a simple regression. And so the variance of beta 1 tilde is the sigma squared divided by SST for the x variable for the first variable. That's the formula coming from the simple regression. If we think about what is the variance here when we have another independent variable, that is almost the same expression, but we're multiplying this times 1 minus the r1 squared. That's the regression of the r squared coming from the regression of the first independent variable on the second one. So in this case, notice what happens. If this r squared is always a positive number, this means this would always be less than 1. This would mean that this whole expression will be multiplied by more than 1. So that's why this whole expression is more than this expression, is a higher value. So what we found here is that if we actually omit a variable, the variance of the coefficient of the remaining variable would be smaller than what it would have been otherwise. So there's a trade-off between bias and variance. So omitted variables leads to a misspecified model and biased coefficients. So we know that we have an omitted variable bias from a few slides ago. That's undesirable. But these coefficients also have low variance, as is shown here, so that is desirable. So in general, how to decide whether to include a variable or not? So it's typically better to have an unbiased coefficient first. So look for unbiasedness first, and then lower the variance or the precision. So in general, it is better to include an independent variable in the model. But if that variable is not relevant or it's irrelevant, then they should not be included because they will not cause a bias, but the variance, if we have more variable in the models, would be higher than if we have fewer variables in the model. So again, include variables in the model, because otherwise if you don't include them and they belong in the model, that would lead to biased coefficients. But if they don't belong in the model, then definitely don't include them, because by including that, you were just going to increase this variance of the coefficients. Okay, so let's give you an example, and that's exactly the same example as the omitted variable bias. So here is the correctly specified model of wage depending on education and ability. So that's the model that we have here. These are the coefficients that we talked about before. And here's a model where wage is only regressed on education, but we are skipping ability. So that ability is omitted and therefore is missing from the regression, omitted variable. So we talked about how this coefficient is biased, and this coefficient here overestimates the effect of education. But also note what happens to the standard errors. These numbers here, the standard errors in the parentheses. And here we have that the model that is correctly specified has higher variance or higher standard error, and here it has a lower standard error. Um, so again, the standard error is the square root of the variance. So the correctly specified model, actually, one of the drawbacks is that it does have a higher standard error, which is not desirable. Okay, so ending with the Gauss Markov theorem, and what that says is that under assumptions 1 through 5, and these assumptions again are linearity in parameters, random sampling, no perfect collinearity, zero conditional mean, and homoscedasticity, the OLS estimators are the best linear unbiased estimators of the coefficient. So best linear unbiased estimators is abbreviated as blue of the coefficient. So what does linear mean? Notice that linear here means different. Estimators are linear in the dependent variable. So if you recall, we had this is the formula for the coefficient in simple regression. And so here we have the covariance of x and y divided by the variance of x. So notice here that here this is the y variable, and all of these other terms here are multiplying this y variable. But this y variable enters linearly here, and it's almost the same expression as wij times yi, where this wij, these are basically some terms or weights that are modifying the yi. So here it means that the estimators are linear in the dependent variable. So again, this is a linear expression in terms of y. So notice that this is not linearity in parameters that we talked about before the assumption. This is when we say that the OLS estimators are blue, the best linear unbiased estimators, what we mean here by linear is that these estimators are linear in the dependent variable. And from all these linear estimators, the OLS estimators have the lowest variance amongst them. So best here means lowest variance. So this is what the word best mean. So again, best lowest variance, linear mean linear in the dependent variable, unbiased, well, because there's no bias, and estimators is, well, they're the estimators of the population parameters. So we define all of these. So again, the Gauss Markov theorem says that under these 5 assumptions, the reasons why we have these 5 assumptions is because they're very, very desirable properties of the OLS estimators. And this desirable property is that they're blue, best linear unbiased estimator. So here are the review questions for this presentation. So define the regression model, estimated coefficients and residuals. Which model do we use to estimate the coefficients? What are the properties? Explaining goodness of fit measures. Distinguish between perfect collinearity and multicollinearity. Explaining omitted variable bias. And then listing and explaining the 5 Gauss Markov assumptions, which ones are needed for the unbiasedness, which ones are needed to calculate the variance, and to explain the Gauss Markov theorem. So thanks very much for listening.